where I left off yesterday. Um, okay, the recording has started. Okay, so thank you everyone for coming back for more discussion of applications of curves over finite fields in cryptography. So I wanted to start with a kind of an open-ended perspective, which is, what is the future of curves in cryptography? So just to kind of review a couple of applications that I was talking about yesterday, in terms of the timeline. So elliptic curve cryptography based on the discrete logarithm problem was proposed in the mid 80s and really started to be deployed in the industry worldwide around 2006, thanks to the Suite B requirements that came out, US government requirements for US government contractors, which pushed the use of elliptic curve crypto into, for example, Windows at Microsoft and around the world, a lot of different deployments. So that was actually only about 15 years ago, but so I spent a lot of my time in the early 2000s working on the building elliptic curve crypto solutions and the release on different platforms. And so zoom forward to 2016, that's when new US government regulations came out, the CNSA requirements, and they increased the minimum bit length for elliptic curve cryptography from 256 to 384 bits. But they also advised at that time that adoption of ECC was no longer required. And presumably that was because of the pending NIST competition to select post-quantum crypto candidates. So the reason for that is even going back to, the mid 90s, Shor's algorithm was discovered, but then already going back to 2003, results of Proust and Zalka estimated that the time to attack elliptic curve discrete logarithm problem on a full-scale quantum computer would be roughly O of n cubed, where n is the log of p. So as you can see, these systems would no longer be secure in the face of quantum computers being built at scale. And in fact, in kind of an update to the Proust-Zalka work with the Quark quantum algorithms team at Microsoft Research in 2019, we had an AsiaCrypt paper, which actually simulates the entire attack on elliptic curve crypto using the quantum simulation code that they had built in that team. And we confirmed these O of n cubed estimates, but also made the constants very precise and quantified like the number of Toffoli gates and the depth of the circuits required. And so once a quantum computer can be actually realized at scale and can do computation which is reliable, then elliptic curve cryptography really will be broken. So thus the move to think about, and that also will apply to higher genus curves, although we have not done such precise estimates of the actual time and space requirements in order to break like higher genus curves, Jacobians of higher genus curves. Sorry, there's a garbage truck going by. So thus the NIST, the National Institute of Standards and Technology in the US, launched a 5-year competition for 2017 through 2022. We hope it will end in 2022 to select post-quantum solutions. So one of the solutions that has been submitted and studied in the NIST competition is based on our proposal from 2006 of a supersingular isogeny graphs in cryptography. So the idea behind these graphs, many of you have probably heard me talk about this before, we proposed a new cryptographic hash function in 2005 at the NIST hash function competition based on supersingular isogeny graphs. And this was joint work with Dennis Charles and Eyal Goren. And so the graphs that we proposed to use there were several, but one of them was this supersingular isogeny graph. So this is a graph where the isomorphism classes of supersingular elliptic curves modulo p are the vertices. So they can be labeled, because they're isomorphism classes, they can be labeled by the J invariants. So you can just think of the J invariants of supersingular elliptic curves mod p. And each one of those isomorphism classes will have a representative, which is defined at most over fp squared. So the curves will either be defined over fp or fp squared. And at that time, we took p to be roughly 2 to the power 256 to allow for generic attacks, so that they would have they would reach the 128-bit security level, because the size of the graph is known to be roughly p, so p over 12 plus a very small correction. And so I've told you what the vertices are of this graph, and then the edges are actually degree L isogenies between these elliptic curves, where L is prime and in particular co-prime to P. But you don't have to worry too much about that co-primality requirement, because P is extremely large of cryptographic size. Like I said, a prime somewhere at least around 256 bits, whereas L is a small prime, like L is equal to 2 or 3, typically in the applications. And so there's no worry that it won't be co-prime to the characteristic. And in that case, when L is prime, you get that the graph has, so there's L plus 1 subgroups of distinct subgroups of size L of the L torsion on the elliptic curve. And so it's actually an L plus 1 regular graph, because you can quotient by any one of those L torsion subgroups. So for example, if L is 2, you just have a 3 regular graph, where when I say 3 regular, I always have in mind that we put the condition that P is congruent to 1 mod 12, which means that there's no really extra weird automorphisms on any of the nodes of the graph. And so you can collapse an outgoing edge with an incoming edge, because you can just kind of associate an isogeny with its dual, so that it becomes an undirected graph. Now, the truth is that looking at this requirement, there aren't that many nodes that have a weird extra kind of automorphism associated with them. So it's not, while we need this condition in order, strictly speaking, in order to say that these graphs are Ramanujan, in fact, if you ignore this anomaly at a couple of nodes, you can think of this condition as being true more generally. And another important point about these graphs that we specified in our original paper is that if you put extra conditions on the prime P, then there will be no small cycles. And small cycles could be, they may be hard to find, even if they exist, but small cycles could be problematic, specifically for attacking the hash function, but also in other situations such as the key exchange. It's not known what type of insecurities might be introduced if you have small cycles in the graph. So these graphs, I like to show this picture because, first of all, it was published in 2008 in Science magazine in an article about our hash function. And it shows a version of the graph. This is the supersingular isogeny graph, where P is, I think P is like 2521, 2,521, something like that. So you can see from the Eichler class number formula that if you divide P by 12, you're expecting somewhere around 200 vertices in this graph. And indeed, you see a lot of little circles here, which are all supposed to be separate vertices in the graph. But what you should also see is that it's very hard to see any kind of structure in this graph. All of these edges seem kind of random, and it seems kind of hard to navigate to find any kind of real direction in this graph. And so what we did was to show a cycle, which is depicted in red here. If you didn't have the red, it would be hard to see, you know, that there was a cycle there. And then we also showed two nodes. I think it's node number 1 and number 24, just random nodes, what it looks like to find a path between these two nodes. And as again, you can see it's kind of a counterintuitive path. There's no obvious direction to get from. It's not like a tree where you know what direction that you're going in. And so I like to show that this is a very, very small graph, like I said, with just around 200 nodes, whereas for crypto applications, we would take a graph of size like 2 to the 256. And an important point is that you don't have to write down the whole graph, because we know that the vertices correspond to elliptic curves, you know, with their J invariants, and then you know how to, we have very explicit, easy formulas for walking around the graph with two isogenies, for example, using Velu's formulas. And so it's very easy to navigate around this graph and specify nodes without writing the whole graph down, which is very important because you wouldn't be able to do that. So just to kind of highlight here that the hard problem that we introduced was what we called routing in the graph, which means, you know, given two random nodes, can you find a path between them? And so for example, the supersingular isogeny key exchange, which was introduced by Zhao and DeFeo and Plout in 2009, published in 2011, was they stated a bunch of other hard problems, but it also just is reducible to the same hard problem of routing in the graph. And since then, there's, you know, quite a few other systems that have been proposed and explored. And in particular, another version of the hard problem. So in a 2019 Eurocrypt paper with Eisentrager and Morrison and Hallgren and Petit, we showed that it's essentially equivalent to being able to compute the endomorphism ring of supersingular elliptic curves as maximal orders in a quaternion algebra. And that's essentially because you can then use the efficient algorithm that we published in Ants in 2014 with Cole and Petit and Tignol to attack the system, basically to be able to find paths in this graph when you describe the graph in terms of maximal orders. So that's kind of a little snapshot of the situation today with supersingular isogeny graphs. In the 5-year ongoing NIST competition, it's actually a third round candidate listed now as an alternate or an alternative. And it's labeled as requiring more study. So I'll take that as a perfect encouragement for more people to work on this hard problem of being able to find isogenies between supersingular elliptic curves. In fact, I noticed, I think there's going to be at least two talks next week at AGCT on this topic. Kirsten Eisentrager talking about computing endomorphism rings, and Anna Maria Yetzi talking about our Wine3 project on using the Bruhau-Titz tree as an approach to trying to attack this graph. Okay, so I thought I would also switch gears here for a minute and go back to a topic that I didn't have a lot of time for yesterday, and that was genus 3 curves. There was some discussion in the question period after my talk yesterday, but I also noticed there was some discussion in the Zulip chat. So I thought it would be worth kind of summarizing what we had said yesterday about the genus 3 situation. So again, I mean, all of the curve-based discrete logarithm problems would be susceptible to quantum attacks if a quantum computer is realized. So this doesn't change that. I'm not making any comment on, quantum for genus 3. I'm simply talking about classical attacks on genus 3 curves here. So going back to just looking at the classical attack. So if you just recall that a generic attack like the Pollard row attack would run in square root of the group size. So since the group size would be roughly Q cubed, the Pollard row attack, the running time would be roughly Q to the 3/2. But I think I saw a comment, I think from Drew Sutherland in the Zulip that, the important point is that you also have to take into account the amount of space that it takes you to run such attacks. And so Pollard row is very efficient from the point of view of space complexity. So, you can store, a small number of distinguished points and things like that. And so it doesn't take a gigantic amount of space. And so the problem with some of the other algorithms that have been proposed, even when they improve on the running time, the space requirements for the factor base are gigantic. And so that's one issue. But another issue is that often the running time estimates are just given as twiddle. So here, and I'm not even making the twiddle explicit in the Pollard row case, but if you look at the Gaudry attack that I mentioned yesterday, Gaudry, Tomei, Thériault, and Diem from 2007, I mentioned that it had like an twiddle of Q to the 4/3 running time. And the issue is that does not really tell you what are the extra log factors and what are the extra constants and things like that. So that when you take a specific target size for Q in order to achieve, for example, 128-bit security, and you go through and you add in all of those log factors and things, just even the running time is not actually better than the generic algorithm. Now, of course, the whole point of asymptotic, asymptotic running time estimates is that as Q goes to infinity, of course, it's going to be much, much better attack than a Q to the 3/2 attack. But the point is that if you, fix Q to try to achieve 128 bits of security, you'll end up picking Q to be around 115 bits, so 2 to the 115 roughly. And at that level, that even for hyperelliptic curves, this is not better than the Pollard row, and that's not even considering space requirements to run the attack. But so be that as it may, an interesting question raised by the paper of Ben Smith in 2008 is that you could move a discrete logarithm problem from the hyperelliptic case via isogenies over to the quartic case. So genus 3 curves will either be realized with a hyperelliptic model or as a plane quartic curve in the non-hyperelliptic case. And so the question was, well, what if you move from the hyperelliptic case over to the plane quartic case? And there we have this attack by Klaus Diem from 2006, which had a running time of twiddle of Q. Unfortunately, again, the space requirements are very significant. So roughly twiddle of Q to the 3/4, so the space requirements. And so this was the paper that I mentioned with Kim Leine from yesterday. Thanks, Drew, for putting the link in the Zulip, where we, slightly improved Diem's algorithm, and we also showed that you could make some time memory trade-offs to make things a little bit better. Also, you could parallelize things to make things a little bit better, but still, even even with our improved version of Deem's algorithm, it's still not better than the generic attack in terms of time complexity, and definitely not in terms of space complexity. Again, the reason for the time complexity is because of the all the extra kind of log factors and constants that are not included in the O-twiddle notation. So I just kind of wanted to take a few minutes, since that was one of the questions from yesterday and the discussion, to address that. And then finally, what I wanted to do is kind of give a list of open problems in this area. And interestingly, this is actually a list that I gave in a talk that I gave about 6 years ago at Brown in the algebraic geometry seminar at Agnes. And I admit I reordered the problems a little bit here, but they're basically the same problems that I stated in that talk. And there hasn't been a heck of a lot of progress on any of them. So I would say, I mean, a lot of these are still, really, really hard problems. And I think that it's really worth working on these problems. So let me just take 1 second to make a little plug here. I hope making a plug is allowed. I should probably have put the link on the Zulip. But I have noticed that there's an issue, like a kind of a community issue, which is that it's hard for mathematicians really to publish in crypto conferences. And that's the main place where crypto results are published. And so, there's not as much incentive for working on, hard crypto problems from a mathematics point of view, because both crypto conferences they've gotten a little better, but they're not very good at accepting math papers, because most of the reviewers are not mathematicians and they don't understand the math. And so most papers don't get into the top crypto conferences. Also, doing cryptanalysis of these systems is incredibly hard, and you usually work for months or years and you get some kind of like minor result. It's not an easy thing to do. It's not an easy thing to give as a problem to a student either, where you don't want it to be high risk for the student. And so a couple of years ago with my colleague, Jung-Hee Cheon, we came up with a plan to launch a new workshop, which is called MathCrypt. I think many of you have heard of it, and hopefully you've heard of it and have helped with both reviewing and being on the program committee and submitting your papers. But this, we canceled last year because of COVID, but we're going to run it remotely this year. And the submission deadline is coming up in early June. So I just wanted to make a plug that MathCrypt is a place where we want to publish in, first of all, the papers appear in a journal, which seems to be better for mathematicians than appearing in a conference proceedings. And also the intention is to bring together people who have done any kind of partial results, even negative results on attacking systems, to kind of lower the bar for publication of cryptanalysis results. So all of these problems that I've listed here are pretty hard problems in cryptanalysis. So the first one is what I just mentioned with regard to supersingular isogeny graphs, which is, the main hard problem there is being able to find isogenies between find an isogeny between two random elliptic curves. There's also a problem of making the isogeny graphs in higher dimensions more concrete. There's been some work by Ben Smith and others on making it concrete in terms of genus 2 curves, but there's lots more interesting work to be done there. Obviously, the elliptic curve discrete logarithm problem, the best known classical attacks are still basically the generic ones, exponential time attacks. Generating curves for cryptography, I mentioned yesterday the CM method. And the CM method is a pretty inefficient way to generate good curves. Also, point counting is pretty high cost way. So generating curves in a more efficient way is still an open problem. Here's a really important one, V-pairing inversion. So if you're able to fix one base point and then make a map which takes the pairing of that point with other points on the curve, and the target, the range is the multiplicative group of a finite field, to be able to invert that map. If you could do Weil pairing inversion, then you would break all of the known pairing-based crypto systems. And then, so the last three I've mentioned are more in the realm of kind of, computational number theory problems that would be, kind of nice to have. They would all be building blocks for other types of solutions. But in terms of cryptanalysis, I would say, number 1, 3, and 5 are all really hard open problems that I think it would be great for the community to be thinking and working more about. So I think I've pretty much used up my time here, even though I intended to leave more time for questions and discussion. But in case, we can take extra time, I think this would be a good time to open it up for questions and discussions. So thank you.
Thank you, Kristin. We do have plenty of time for questions. If anyone has any that they just want to jump right in, go ahead.
So I can go in, I think. Go. Is it okay if I go, Elisa? Okay. Maybe it'll be quick or not, but you mentioned, like, right on this slide, the generating curves for cryptography problem, which I also think is important. But I was wondering if people would post some references in the Zulip, maybe, if you can, on why it's important. I actually just submitted, last year submitted a grant where I was like proposing a method to attack this, and the comments came back on my grant saying that they didn't see the interest in solving this problem. So I'd be interested if people had more supporting evidence of what it would do for us to be able to generate elliptic curves with prescribed numbers of points over finite fields, say.
So were you specifically talking about elliptic curves, Christelle, or were you thinking about like genus 2 or genus 3?
It was specifically elliptic curves, yeah.
Yeah, so I think the issue is that because elliptic curve cryptography is pretty mature in terms of being standardized, there's been a whole sequence of efforts to standardize elliptic curve crypto, which includes the NIST prime curves that are specified for different security levels. So there's, P256, P384, P512, and then there's the Koblitz curves, and then the blah, blah, blah. So I think what happens is that because there are existing standard curves that are used in the industry, that people probably think, oh, well, we don't need to solve that problem. So I would kind of push back a little bit. I would say, first of all, pairing-based applications are very interesting and important, although they are not widely deployed. Things like attribute-based encryption, identity-based encryption, short signatures, these are all very, very standard pairing-based crypto applications that could be useful in a range of settings. And so there are standard, pairing-based families as well, like for embedding degree, 6 and 12 in particular. But there's, still more possibilities there. And then I would just say that, I don't know, anybody else have any other good ideas?
But thank you.
If I can add an idea to that, and it's sort of a natural outgrowth of the pairing-based curves that we need. In the last few years, there are more and more curves that are being sort of developed or invented or being given funny names in like a zero knowledge, where people want a secure curve over a finite field, which is actually the order of a pairing-based group. Because your curve is, your crypto system is not going to be run on like a PC architecture or something. It's going to be run on a sort of in a zero knowledge proof system instead. I mean, years ago, I was trying to teach elliptic curve cryptography, and a lot of people would say, well, why do you need to teach us Scoff's algorithm? Because the curves have been standardized. We're just going to use these. I don't need to find a new secure curve. But then a couple of years later, you could say, well, we're looking at generating new curves for TLS 1.3, like standards evolve.
Yep.
Standards are never forever anyway. So, anyway.
Thanks.
Just to echo what
Drew, do
Ben
you want-
said.
Okay.
Yeah, the one case I know, Christelle, of where I was using the CM method sort of really in earnest, where I really had to push up to a large class number CM field, was for a cryptocurrency application. People working on zero knowledge proof protocols, and they wanted pairing friendly curves with some very specific properties, and they needed to handle large discriminants. But I was also going to mention there's another application for even just for the old-fashioned CM method, which is for elliptic curve primality proving. If you have a better way where you can more efficiently construct elliptic curves with known order, you can use the Akin-Morin you could speed that up and potentially be able to prove primality of primes that we currently are currently out of reach. I think the current standard for ECPP is around 30,000 digits, but I know there are a few like Cunningham factors that people would like to know are prime, but can't actually prove a prime right now.
Awesome, thanks.
So one related question is, what are the features we're looking for in curves? Is it just group size, or are there, people have mentioned kind of friendliness to the Bay pairing.
Yeah, so actually that's a good point. I'm sorry, who asked that question? I couldn't see, it didn't show me.
David Rowe.
Oh, hi, David.
Hey.
Ben's comment reminded me of something that we often sweep under the table. And that is that what happens with pairing friendly, quote unquote, friendly curves is that what you actually need, you're going to need to work over the finite field extension where all the torsion is defined, and the torsion that you're going to work with for basically the group that you're going to need to work in. So the problem is that can happen in several different ways. So if you think of the end torsion on the elliptic curve as having two pieces, it's rank 2. So it can be that like, I think all 4 possibilities are possible. And I think we even have names for these different 4 cases, but I've forgotten the names. So you can have one piece defined over the base field, FP, and one over the extension field like FP to the 12, or you could have both over FP to the 12, or you could have, and so they actually have different security properties depending on where that torsion is defined. And so that's an important thing to think about. And I'm not going to give you like a whole summary of all the different cases right now, but that is definitely a consideration. And it does matter when you're generating these things. Those two things are related. So that's one answer. Maybe other people have other answers, but that's one property that I was thinking of. Okay, I'll throw out another one. So we often make the operations for the crypto system on the elliptic curve so much more efficient by taking special primes. So primes that are close to a power of 2, for example, like Mersenne primes or generalized Mersenne primes. And so that's another thing that you can look for, is how can you simultaneously make the operation's really efficient by having these really nice primes that you use. I think there's probably a couple more things like that you could come up with if you keep thinking about it. It looks like, I can't quite tell, but it looks like Elisa, do you have your hand up?
Yeah, I was going to say Lisa has a hand up.
Okay, good.
It's been there for a while.
Yeah, actually, I mean, I would like to know a little bit more about what you mean in your point 6, modular invariance of genus 3 curves, because, well, I mean, maybe explain me how, because, I mean, I have a paper from last year in which I give expression of genus 3 hyperelliptic curves invariance in terms of the theta constants. So I suspect that this is what you mean by modular invariance. And also Christophe and Renal have one, also from last year, for this mirror invariance for plane quartics.
Great, thank you for mentioning that, Elisa. So actually, like I said, this list is from a talk I gave 6 years ago. So, and I hesitated whether to leave that one on there, but if I took it off, then I wouldn't be able to claim that the list was the same. So, but anyway, I mean, we also had, to some extent, like the paper with you and the, you know, Serena and Christelle and Adelina and Pinar and Micah, I think I got everyone, that has a modular invariance suggested, but not, you know, I'm sure they don't have probably as good of the properties as the one you mentioned. So maybe you could put the link to your paper either in the chat or in the Zulip or both. And also the one, I knew that Christoph was doing work on this direction too, but I didn't have the current reference. So that'd be great if you could put those in there. And anyone else who's working on this, I mean, this question of modular invariant, or well, in general, the question of invariance for genus 3 is very interesting, right? So if you restrict to the hyperelliptic case, you have, you know, the kind of, you know, Rosenheim invariance or, you know, things that are very, very typical. But then the quartic case, you know, you have different things like the, you know, Scioto invariance or whatever. Those are the things that were known long ago when I was actually working on in this area. And now being able to have new ones and also being able to have invariants that span both cases. So that is really interesting. Do any of the work that you're mentioning actually handle both cases at the same time?
Not and yes. So let me explain it. Like, no, because we do it separately. So I did the genus 3 hyperelliptic ones. They did the plane quartics. But somehow, because we managed to express those invariants in terms of Siegel modular functions, somehow we only need to compare. So, I mean, it's not done, but I think that we could like kind of easily do it. Like saying, oh, look, this invariant for the plane quartics should be like the equivalent for this one for the hyperelliptic ones, because when you look at the modular expression, so the Siegel modular function that corresponds is actually the same one. So you could say that this invariant, like, I mean, it's like a unified invariant, if you want.
Oh, great. That's good to know. Thank you. So that would mean that you could, go back and forth, like if you need, if you could generate, like if you could recognize theta values up to enough precision that you'd be able to use either of those sets of invariants, right?
Yeah, yeah.
Nice.
Actually, because I have the micro open, I guess I can ask another question that is not related with this one. That is like, I mean, you didn't mention it in this list, but I heard that it's also kind of a difficult crypto problem related with curves. That is the one about generating random supersingular elliptic curves. So I guess that this is like getting randomly in a point on the isogeny graph. So do you have any idea about how this problem should be attacked, or if it is really like something that is important or not?
Yeah, well, I actually do think it's important because the problem is that, so essentially, if you know what I think we even included this in our 2019 Eurocrypt paper, like if you know a path to one of the special elliptic curves where you know the endomorphism ring as a maximal order in the quaternion algebra, then you can kind of pull that back along the path in a sense. And so it's very hard at the current status to know, like, you know, whether somebody has put in a backdoor, like a trap door to a system. And we certainly don't have any way to like certify that you haven't. I think that I mean, to be able to, what would be nice, like the ideal solution would be that if you could have something like what they actually did for the NIST curves, where they took some random number generator and then they took some random seed, like, you know, today's date or something like that. And then they took the output from the random number generator from that seed. And then they showed that they had like constructed the curve. Now, of course, it could be that there, you know, was still some way of engineering some backdoor into that. But, you know, that would be ideal, is if we could, you know, you could basically take a random value and use that to pick a random, you know, super singular elliptic curve. And so that should probably be added to this list of problems. That's a good one.
Thank you.
Thinking about David question, I mean, maybe, I mean, there are other properties sometimes one is interested in. I mean, I think it's more for the fun of math than for the user of crypto, but I mean, in order to not have side channel attacks, sometimes you want a unified law on the abelian variety, and then you need to do like what is called completeness. And then, I mean, it pushes you to design very special embedding of your curves or abelian varieties inside some projective spaces. So that's sometimes another kind of game that you can play. And also, I mean, I mentioned it yesterday, and I thought that also at some time Ben was really super interested in it and trying to understand what was going on. I mean, this trillionaire map from Wang, and I'm still not sure what is the current status of that and what kind of property you ask really about this abelian threefold or even fourfold maybe.
I think this was Alice Silverberg and some people were working on this, and I forget all of the co-authors, but yeah, you want like a trilinear map instead of a bilinear map like the Weil pairing. And cryptographers are interested in this because the idea is if you've got this, you can kind of do everything else. It's one of these kind of magic tools, which for theoreticians, you can build everything out of a trilinear map. The proposal that they have, the third argument is, I think, basically some sort of a polarization, or it's an element of the Néron-Severi group on an abelian surface, I think, if I remember correctly. But we discussed this at this meeting in at Brown University last year or the year before last. You know, back in the days where people actually saw each other face to face. So I can't remember when this was anymore. And there was some very rapid objections at the time to, you know, to the security of this, or like really to the making this work somehow. So it's still a really, really interesting open problem. I think if anyone can come up with an efficient trilinear map that's where all three of the arguments are hard to invert.
Thanks for the update.
Sorry, go ahead.
Yeah, no, sorry, I unshared my slides just so that I could see people better.
We've got Drew has his hand up.
Yeah, I was just curious. This is maybe feeding off some of the other questions, but it seems to me like one big problem in the cryptocurrency world anyway today is thinking about how to make blockchain protocols that don't consume so much energy, that avoid using proof of work. And I was wondering if I mean, I could imagine there might be opportunities like zero knowledge proofs might play a role in coming up with new protocols that would provide the benefits without the cost, the economic or the environmental cost of proof of work. And I assume you probably know a lot more about this than I do. I was wondering if you had any comments or were aware of any work along those lines.
Well, I do, but unfortunately, it's not a very mathematical comment. I'm actually equally concerned about the unnecessary energy consumption for this type of system. And so what I think is that I mean, even for like cryptocurrency where you want to make micropayments available to the developing world and things like that, I really think that a centralized system which basically backs or guarantees the currency, so you have a certain number of parties in practice, you have a certain number of parties investing, basically providing the financial backing for these currencies anyway. And I just don't feel that we need to allow mining as a way to create currency. I think that they can just put a distributed currency out there backed by a small number of parties that have basically agreed to work together. And I am 100% against allowing mining to solve this type of problem. I think it's unnecessary. If there were a mathematical solution, that could also be interesting, but I don't know one. I'll be honest, I haven't thought about it. Maybe I'll think about it.
It seems like something that would look good in a grant proposal anyway, if you're going
It
to.
would, but I just think there's such a better solution available to us, which is that all the banks that are each putting $100 million behind this currency just agree to cooperate and run the currency. And that's it. No mining needed.
It's probably a good point to jump in again. And I mean, again, the channel's open. We can continue talking here and also on the Zulip, where we can post more questions and answers and references. But we should take a moment to virtually clap again for Kristin. Thanks for the time and all of your answers and sharing your knowledge.
Thanks, everyone. If you have any other comments or questions, put them in the Zulip and I'll check it again later today and tomorrow.
So for those of you that are going for dinner or lunch or beer or whatever, I believe the next fascinating talk, well, it's the next talk. I don't mean there's any non-fascinating ones. Will be in 1 hour and 10 minutes.
Great, thank you, bye.
Thanks.